guys are the brave ones. Campus seems deserted. Surprising. Okay, so it was great to spend time in the lab with everybody yesterday and Monday because I got questions where everybody stands. And so we know, it seems like everybody's pretty much on track that everybody's going to be plan on generating all their data next week, it seems like, right? And so we have either Monday, Wednesday, or Tuesday, Thursday next week, so that's 2 lab sections to try to finish things off, and then it's Monday or the Tuesday the following week, and then at the end of that we get to Thursday and Friday for the oral presentations, and I think I have a schedule that we'll use Thursday during the lab time to do it. I know at least Tuesday, Thursday people have that time available. I'll use Friday for the lecture time, but go beyond that to fit everything in. And I think most people have, Monday, Wednesday at least, have that available because of walking the time out. I'm going to ask that everybody come to both days, unless you have a conflict that you talk to me about beforehand. And I'll talk about next week about a little more details about how to be structuring your presentation and an abstract, and you're going to be sending me your proposal. It's an outline. 3 things I've asked them to do for this lab: the abstract, the proposal, and of course the oral presentation, PowerPoint. This you're going to be providing to me by the end. This you've already tentatively drafted, but you revised it, or you will revise it, because you know more now than you did when you were proposing things, but you'll submit it as a proposal with the approach that reflects what you actually are doing or did. And this, of course, we surmise. In the lab for this, it's important, in my opinion, to try to generate all your data, if at all possible, by the end of next week, because in most cases, all the things I've seen from everybody, the data analysis part will be a little bit more involved for many of you than it may have been in the past, and I think all of you have done a nice job of stating some testable hypotheses, and implicit in a testable hypothesis is testing the hypothesis statistically in some way to actually accept or reject the hypothesis. And so for the data you generate by the end of next week, ideally, you'll need to do all the, of course, the manipulation to get it in a form that you can do some statistical analysis. And if people have not had any experience with statistical analyses, then these days will be key in coming in with your data to perform some of those simple statistical analyses. Has anybody done any statistical analysis of data before? No? Nothing at all? I think most of you, if you have just two kinds of groups, two sites, two this, two that, you can probably do things with a simple t-test that you can do in Excel. But if you have multiple sites or groups, you'll need to maybe use some other kind of statistical software that I can help you with, the T's can help you with in class. You say something?
Well, I was actually going to ask, so does that mean that during finals week we're not going to have anything else?
That's correct. You will to be done by Friday. Just the last week's class. Okay. Any questions about any of that stuff? So today I'm going to talk more about mass spectrometry, and I don't think I'll get into it. And next week I'll talk a little bit about MALDI mass spectrometry. Now, the mass spectrometers that you saw this week and last week are atomic or elemental mass spectrometers, meaning they're measuring elements. And of course, there's a whole discipline of mass spectrometry that revolves around measuring molecules, like small organic molecules. And the MALDI mass spectrometer is one good example of that I'm going to talk a little bit about. And then we're going to finish in the class talking about today electrochemistry, because it's such a pervasive, important area of analytical chemistry that I want to make sure we talk a little bit about that. We used to do a lab on this. It didn't reliably work. One of the instruments in the lab, but it's still important enough to talk about here. Okay, so we stopped here last time.
Are the grades going to be curved for the class?
The grades can be curved for the class. It depends on what the distribution of scores is for the class. It's rarely is it a straight, 80, 90 distribution. It's a curve to be kind of bit on curves right over the scores.
Can you get extra credit if you do a lab report curve?
Good question.
I think everybody's doing pretty well, my sense is, and I think everybody's pretty much right where you should be. You always want to do better at certain things, but there's nothing that's, I've had classes in the past where there are some students who are just really struggling. That doesn't seem to be all the case. Okay, so I'm not going to reiterate this much more other than to say, these detectors that we're measuring in mass spectrometry, obviously we're measuring atoms, right? We're measuring ions, we're measuring individual elements. That's a key distinguishing feature compared to the other methods we've looked at that are measuring photons or the absence of photons, for example, or conductance or some other indirect measure. And I finished last time of saying in these mass spectrometers, there's typically a type of detector or multiple detectors of this type that have some type of conducting dynode surface. What that means is that it's essentially, it's not conducting electricity, but it's converting, maybe a better word might be a converting dynode. It's converting one type of signal, the ion that you're generating from the plasma, into a different kind of signal, which is the electrons. And so this converting or conducting dynode surface then is a special surface in the beginning that when an ion impacts it, it releases electrons, then it can get accelerated via differential potentials across these different dynode surfaces. It gets accelerated and then strikes here, more electrons get emitted and strikes here more, and it magnifies that signal. So by the time you get an output potential, electric potential, a current down here, you are turning one ion event into about 1 million electron events that are released. And so that huge benefit of that, of course, is that it greatly magnifies that signal. And it's what allows us to measure the impact of a single ion. Otherwise, we would never be able to measure the impact of a single ion. And so there's multiple kinds of these detectors. Some have these differentially arrayed dynode surfaces. Some have a continuous surface like this, but they achieve the same end. They take an individual ion input and they magnify that substantially as a current that's measured. Okay? That's a key feature. And I think I say all that here. The key for you to remember is that one ion amplification, one impact of an ion is generating the secondary electrons that are greatly magnified as they get accelerated down the dynamic cascade. That just reiterates what I just said. Okay, now, mass spectrometry. This is something that I want to pay close attention to. Mass spectrometry, of course, relies on separated masses. That's it. And the ability of mass spectrometers to separate masses can be dependent largely on what main feature, would be my guess. What?
Mass ratio.
Right. So it's separating masses based on their mass to charge ratio. But what part of the mass spectrometer is doing that? And what's it used to do that?
Quadrupole.
So it's via magnetic field, right? And the magnetic field can be generated a number of different ways. One is a quadrupole, and one is a magnet. And the ability of a quadrupole to generate a strong and stable magnetic field is less effective than a magnet may be able to generate, a large magnet. And so the magnets on the higher end mass spectrometers that are magnetic sector, so you'll sometimes hear referred to mass spectrometers as a magnetic sector mass spec. That means it has a large magnet. Those magnets can be about this big around, so they're really large. And the flight tube, you'd have a magnet like this, and the other pole a magnet like this, and the flight tube that the ions are being accelerated through go down the middle of the two poles of the magnet. Each magnet pole is essentially like this thick, this big around. They're like two pancakes on top of each other. The flight tube goes between. Okay. So it generates a very strong magnetic field. And the features that are necessary for this to be effective is one is you can adjust or vary that magnetic field exactly because you need to know what that is in order to predict how those ions are going to traject down the flight path. And you need to generate a very stable magnetic field because any fluctuations in the magnetic field, of course, will lead to fluctuations in the trajectory of the ions that are being sent down the path. So the quadrupole mass spectrometers are much less effective at doing this than the magnetic sector. And one way that we can evaluate how effective these different mass analyzers, these are both examples of what they refer to as a mass analyzer. And the way that we can evaluate the effectiveness of these mass analyzers to separate ions based on their mass to charge ratio is based on the index of resolution. And so mass resolution essentially refers to the ability to separate two masses effectively. Just like in chromatography, where we had separation resolution of two peaks chromatographically, it's the same concept, where we're evaluating the utility of the mass analyzer to distinguish and separate two adjacent masses. And they can define mass resolution simply as a nominal mass, m, over the difference between two masses, mass 1 minus mass 2. Is essentially the nominal mass over the delta of mass, difference in the mass. And if we had, for example, I'll talk some examples today, if we are interested in using lead isotopes, like I talked about that Claire Patterson guy at Caltech who used the mass spectrometer to separate and analyze different lead isotopes in rocks and meteors in order to first evaluate the true age of the Earth back in the 50s, right? And they had to develop, and they built, at that time they were building them by hand in their labs, their mass spectrometer to do that. And they had to separate lead masses and say lead 206 is one of the lead isotopes. And the exact mass, I don't know, it's not exactly 206, of course. And they had to be able to measure lead 206 separate from lead 207, separate from lead 208, and separate from lead 204. So there are these four stable isotopes of lead they had to separately measure and then look at the relative abundance of these isotopes because they all come from different uranium or thorium progenitors that radioactively decay into these final stable isotopes. And they could then use that decay time and the relative abundance to sort of calculate how old the ore was that these lead isotopes came from. Right? And they could use that in Earth and meteors, and then get an idea of these years. So they had to separate these two. So in the simplest way, if I had to just separate, say, lead 206 from lead 207, I'd calculate a resolution that would say a nominal mass is lead 206, and the mass difference between the two isotopes I have to separate is 1, 206 minus 207, with the absolute value of 1. So in this case, the resolution would be a resolution of 206. If I was able to separate based on just one AMU, but maybe even to a greater degree to say maybe from 0.1 AMU, I can distinguish lead 206.1 versus 206.2, then I'd have a resolution of 2060. And if I needed to separate something even more, so it's 0.01, right? So 0.01 AMU, difference between two adjacent masses, then I'd have a resolution of 20,600. And mass spectrometers vary depending on the kind of mass analyzer they have and the type of resolution that they're able to achieve. And so you saw two mass analyzers, essentially the mass specs you saw in the Marine Analytical Labs. One was a quadrupole that was in the same room as the OES. And quadrupoles typically have a mass resolution of about 200, 200 to 300. And that means they're able to separate two adjacent masses easily by 1 AMU, but not much better than that. And then the mass spectrometer with the magnetic sector that was in the next room has a resolution of, I think, upwards of about 9,000 or so. And so that means it's able to separate masses that are all different by almost 0.01 AMU. And you might ask, why does that even matter? And it's shown right here in this table. So when you look at the actual nominal mass of different isotopes, let's say we will care about arsenic, which is arsenic-75, the actual atomic mass is this. Or if we look at chromium-52, the actual atomic mass is this. Now what happens when you are doing the analyses of samples by mass, especially by ICP mass spectrometry, is you have the presence of two things in relatively high abundance just by virtue of how you do the analysis. And one of those things is argon. Where does that come from?
Instruments.
I don't say the air.
Okay, that's where we pulled it from.
Yeah. Where's the argon coming from?
Argon tank gas used
The plasma is a argon plasma, right? So the argon gas that's being ionized, just so you know, my hand goes back today. The argon gas is coming out of this torch, right? And you've got your sample tube in the middle of that, and then the argon gas is being introduced here, it's swirling around, and when it hits the RF coils here, that generate a very strong radio frequency field, and those argon gas start to kind of move a little bit, but they're not charged, and then you introduce a spark here, like a little lighter, and that spark ionizes a couple small number of argon atoms right next to the spark, and those argon atoms in that radio frequency field get accelerated because they're an ion, and then they slam into other argon atoms, and they get ionized, and they start moving around really fast, and they slam into other argon atoms. Pretty soon, you have a plasma because you get all these argon atoms that are in very high abundance that get ionized in that RF field and start slammed into each other, and they generate, because of those collisional forces, a very hot plasma gas. Okay. And so you have, do you have a question? Okay. So you have now a plasma for the ICP, inductively coupled plasma, because the plasma is generated via an inductively coupled RF coil. You have this plasma gas that's made out of argon. And so that means that anything that's coming through in your sample that reaches that argon plasma gas and then reacts and gets ionized has the potential to react to those extremely high concentration of argon ions there. And what you end up generating, unfortunately, is these polyatomic species. Even though it's hot as 8,000 degrees, you generate these stable polyatomic species that are charged. It's not showing charged, but they are. That are oftentimes with argon or other high concentrations of salts that may be in your sample. So if you're analyzing seawater, which you never try to do, you generate a ton of argon chloride because you've got a ton of chloride in there and a ton of argon in there. And in this case, this argon chloride polyatomic species has a mass that is really close to arsenic 75, right? In fact, it differs by whatever you do the math, but it's about 0.01 AMU. So if you try to analyze arsenic in seawater on a quadrupole mass spec, you'd be screwed, because you'd be like, I'm not measuring arsenic at 75. All I'd be measuring is extremely abundant peak of argon chloride, because I can't separate these two. If I wanted to, I'd have to go to a different kind of mass spectrometer that had a much higher resolution to be able to separate these two. And you can look at this whole table and say, if I'm doing chromium, it's the same issue with chromium oxides. There's also oxygen in the air. It's just for and so for all of these elements, there's these, they call these polyatomic interferences, or just isobaric. Isobaric mean the same mass interferences, like in these cases here. And so you would enter into a scheme and say, my goal is to measure something, one of these isotopes. And when you're using mass spectrometry, you don't just measure iron, you don't just measure copper or whatever, you measure a specific isotope of those elements, right? Because they weigh different amounts. And so the first thing you would do as an analyst, and this is what Rob would do if you went to him for assistance, he'd say, what do you want to do? And you'd say, I want to measure arsenic in groundwater, because I know it's a big problem in some places in the world. And he'd say, well, what's the composition of the water? Has it got salt water intrusion or whatever? And he'd say, I don't know. And he'd sort of make, talk about it. He says, well, first of all, we have to do this on high resolution mass spec, because I know, I can look up on a table, and I know that there is an argon chloride interference that could be significant there if there's high salts there. And you would develop some scheme knowing this. So this information is actually well known. And then you would make choices about what type of instrument you would need in order to achieve the mass resolution necessary, in this case nearly 8,000, resolution of 8,000, to separate these interferences. And that's what we typically do. This essentially makes the same point, talking about other kinds of isotopes will be my measure, and whether they're interfered for by polyatomic, meaning molecules of more than two or more atoms, right? Or isobaric, meaning that there's another isotope of another element that is very close in mass to the isotope that you want to measure. So in both cases, for the isobaric, we have a similar mass, or for the polyatomic, together they make a similar mass. You have to be able to resolve it in order to measure them. And there's tons of interferences that could be issues depending on what kind of sample you have. Okay. So now I'm going to step back and I'm going to talk about a few other strengths of mass spectrometry. Then we're going to talk about some interesting examples to illustrate this. So we've already known a little bit about this. So we know, I think, that the intensity of ion beam can vary with different things. So when I say intensity of an ion beam, what do I mean by that?
Are you talking about the ion beam coming from the sample after the electrons are dropping there?
Yeah.
Talking about
The
frequency?
number of photons hitting the detector.
Or what?
Photons hitting the
No.
detector? Or,
Power?
Ions.
Ions.
Right? We're measuring masses. Don't
Oh, right. This is-
don't leave this class and confuse that, because people come to me and assume that I misled you. We're measuring ions, which are isotopes of an element, right? That has been ionized. It's very different than a photon. Okay, I know you know that, but in terms of the instrumentation, it's very different than how the instrument works. So when I say the intensity of the ion beam, what does that mean? It means that you have a torch, in this case the ICP. It doesn't have to be an ICP. There's other ways to generate an ion beam. Okay. All I have to generate are ions, and there's many ways to generate ions. One of the most common ways is with an ICP. It doesn't couple plasma, but there are other ways. I generate an ion beam, and the instrument entry is right here. That ion beam then gets accelerated through these, what we call, I mentioned just before, these electrostatic plates. Folks, they're just essentially round little plates that have a slit in the middle, and they're polarized on one side of the slit versus the other. And the potential on one plate is, electrical potential increases on these successive plates, so that ions get steered based on the potential applied to each plate on the poles, and they get accelerated from one plate to the next, so that when they enter the mass spec in the high vacuum here, is they have a very high velocity. And so the ion beam intensity, they get accelerated. The ion beam intensity is talking about the ion, the number of ions that are actually striking the detector. And so a higher intensity, of course, a higher number of ions per second, right? They measure that as a count, so ions per second is counted. So now if we look at this and say the intensity of the ion beam, meaning that the number of counts per second that are striking the detector varies with a number of things when you're doing the analysis. Somebody can kind of do this for you. One is a sample matrix, let's say. With the sample matrix, we mean what? This is a different sample matrix. Okay. Other analytes in the sample. What else?
Salt.
Salts, okay. What else?
Well, any particles that are in your matrix that are in your analyte are going to collide with the analyte when they're going through the...
Could be collide, but it could be a lot of things that would be collide. So it's anything in the sample other than your analyte that could be influencing or affecting how your analyte behaves in that analysis.
Couldn't the amount of analyte also change the way that it's detected? Because isn't it possible for the analyte to climb into itself while it's going through the machine?
The assumption is the analyte attains a consistent velocity trajectory from the point at which it's accelerated to the mass spec coordinates to the detector. So they're all moving together, not in a bolus, but they're moving together in essentially in a beam.
Is the beam? I was just wondering if because the tube seemed pretty large when I saw it in Frank's lab, from what I expected. Is it true that the tube is small enough that there's no sort of weird interactions based on the geometry where they are coming out of the straight beam?
Yes, that's the goal.
Okay.
That's right. If they don't come out in a straight beam, they fly out somewhere and they don't hit where they're supposed to hit and get measured. That's right. So we'd say a sample matrix is anything in the sample other than the analyte that could influence the analyte. Okay. Write that down because that's important. And so for those of you measuring caffeine in coffee, well, caffeine's the analyte, and all the other stuff that makes that coffee black is the matrix, right? Including the water that the coffee is in. All that stuff could influence how you're able to measure caffeine. If you're measuring anions in surface water by ion chromatography like you guys are, then all the other stuff that's there, you have no idea what it is. But clearly there's other things there, right? That may be, dissolved organics, a lot of things could be influencing how those things perform within the ion chromatography. So the sample matrix is of course a big issue, and it's not only an issue because a lot of that stuff gets ionized and sent into the mass spec and may influence how the analyte ions are traversing towards the detector via collisions and all these things, right? Because they acquire different velocities based in part on their mass to charge ratio. But also because those different sample matrices components, when they enter the plasma torch, like I said before, they are getting ionized, they are forming other molecules with other species in there, and they are affecting the extent to which they can collide with your analyte species. They absorb thermal energy in that plasma and affect the extent to which your analyte species may even become ionized. Okay? So all those things are important, and that may change over time. You assume that you're aspirating a sample in it and everything's consistent and constant exactly over time, but that's not the case. And so the ion beam intensity can vary as a function of what your sample's like, how that changes from one sample to another, one groundwater to another groundwater, or whatever coffee to another coffee. Things are slightly different. It changes because the plasma temperature fluctuates, because as those components enter the plasma, they're essentially absorbing thermal energy in there that's used to ionize those components. And depending on how much other stuff is in there, determines how much of that thermal energy is absorbed by things other than your analyte. On the instrument, we know there's instrument noise, and we talked about that a little bit. For any detector, whether it's a UV-Vis detector or the ion chromatography with the conductance detector, there's fluctuations, electronic fluctuations in the detector noise, right, that can contribute to that. And with any kind of detector, its sensitivity changes over time, with age. So all these things matter. And then if you have a goal like I was just illustrating to say, if I want to measure lead 204, lead 206, lead 207, and lead 208, and I want to compare the relative abundance of ions that I can measure in a sample from these 4 different isotopes. And I have one detector here that I'm analyzing each isotope. How do I do that? I take a sample from you, a urine sample from you, and I want to know what lead isotopes are in your urine, because I can use that to understand where you got exposed to lead from.
You vary the magnetic field?
Yeah, so you adjust the magnetic field. You say, I'm going to set the settings on the magnet, count, and send 204 here, and do that for 50 milliseconds. And then I'm going to change it quickly, and then I'm going to direct the 206 in, and then I'm going to change it, and then 207 in, and 208, right? And in the time that I measure, even though I may sweep across these 4 isotopes in a matter of a second or two, things change over a second or two. And so maybe the conditions in the plasma, what the sample composition looks like when I'm measuring this versus this might fluctuate a little bit, and that fluctuation is going to affect the uncertainty, the relative noise that I'm measuring in determining these relative amounts of these 4 isotopes in this example. So it can be a problem. So if I were to ask you, you know this answer now, if I were to say, how might we adjust or correct for changes in ion beam detector responses and all that stuff over a long period of time, let's say over minutes, hours, or whatever, of analysis, right? How might I do that?
The standard edition.
Standard edition, no?
The yttrium and.
Okay, what is that? That's not a standard edition.
I mean,
Internal standard.
internal standard.
Internal standard,
Yeah.
right? That's very important. When you do atomic emission spectroscopy, when you do any kind of mass spectrometry with an ICP, and you have an aqueous sample, you always use an internal standard where you add some element, some isotope to your sample, and you're measuring that at the same time, not simultaneously, but you're measuring this. In this case, we might measure thallium 205. And I'll measure thallium 205, and this, and this, and this, and this, and this, and the concentration of this is the exact same in all my samples. And so the abundance, the counts I get for this should be exactly the same from one sample to the next, unless there's an effect of the sample matrix or changes in the plasma stability or whatever, right? And so I can use this to changes in the counts over time to adjust all of these to help correct for those things. So we know that, right? We talked about that. That's fundamental and important. But we can also look at the standpoint of utilizing different isotopes to measure something, what we might regard as probably one of the most accurate means to determine a concentration of an element in a sample. And the method that is used to do this is called this isotope dilution. Now, I started this class off by saying, what is the standard way that we determine concentrations of an analyte in a sample? What do we do? I don't want the details, but what's the fundamental? Generate a standard curve. That's right. You generate a standard curve, and you have a concentration of something, and you have the response of something, and you use that relationship of that external standard curve to measure an unknown, and then interpolate on that standard curve the concentration. And what's the problem with this approach? That essentially 99% of all analytical methods use. What's the problem with that approach? What's the limitation of that approach?
No tricks. Well, it depends on how you make that, I guess. But if it's made from just water and the analyte.
Okay. And what's the underlying limitation of that? Fundamentally.
It has to be linear.
Okay, well, so we assume it's linear, but there's even more important, I want everybody to know this, I'm going to walk around with the eyes. What's the fundamental limitation of this assumption that underlies almost all analytical methods?
The responses linear? Is that the assumption?
Well, that is an assumption, but that's not the big problem.
Your sample will be using the standard.
Your assumption is, exactly right, Nicole, your assumption is that this relationship in these standards is exactly the same in your samples. And is that true? Oftentimes it's not, right? You know that, right? We talked a lot about that. You know that that underlying assumption sometimes is not true. And what do you do?
Method of additions.
Well, and then you hope to God that that corrects for it, right? Maybe it does, maybe it doesn't sometimes. And so, for all analytical methods, we have this underlying limitation in this assumption. And we sometimes go to all these other means to try to prove to ourselves that it fits our samples, and we can use this assumption and save ourselves a lot of time. The ultimate way to get around this is with a method like isotope dilution mass spectrometry. Because this is that Zen thing I was telling you about before, that we'll never quite get there, but we get pretty close with this approach. So you imagine that, in this case, you're using your analyte in some sample that's different, a standard that's different from your sample, to then infer what the concentration is in your sample, based on that relationship. And you might say, ideally, in a perfect world, what I want to do is use the concentration of the analyte in my sample to determine the concentration of the analyte in my sample. And you're like, well, how do I do that? Because that seems like a circular problem, right? Logic. And the way you can get around that is by using a method like isotope dilution mass spectrometry, where you would add an isotope of your analyte to your sample, and you would measure multiple isotopes of your analyte in your sample, and by looking at the relative change in the abundance of those isotopes in a sample that you spiked with an isotope versus not, you can determine exactly what the concentration is. And so when people, like the National Institute of Standards Technology, when they generate those standard reference materials that I ask you to tell me what is one way that you could determine evaluate the accuracy of your analyses, and most of you said you use a standard reference material that you buy from somebody that's been measured by multiple methods. So that's true. That's exactly the answer I was looking for. One of the main ways that they certify those standards is with the technique of isotope dilution mass spectrometry, because it is the gold. And I say the gold standard. That is the way that it's considered to be most accurate. And the way it works is you take a sample, and the assumption is that your analyte exists in at least 2 stable isotopes. If it doesn't, like some things do, like manganese, then you can't do it, right? But most elements have at least 2 stable isotopes. And so what you do is you measure in your sample the relative abundance, this is now just the abundance, percent abundance, of the isotope A and isotope B in your sample. You get this relative measurement. So I've got, 65% of the counts I measured in my sample were A, and 29% were isotope B. Then I buy from the government a spike of my isotope that's been heavily enriched in one of the isotopes, isotope B. And so they use like a synchrotron or some other accelerator facility to generate a sample of highly enriched, it's been highly enriched in one particular isotope, just like they would do if they were enriched uranium or thorium or whatever, right, for different uses. And so you buy this from the government, and you can then you solubilize this, make it dissolve it in weak acid, and then you buy a certain amount, and you know the exact concentration based on what you diluted it to. And then you would add a spike of this, a certain amount, and you know, like 1 nanomole of this, you'd add to your sample, and you create a mixture. And then you would then measure the relative amounts of the isotope A and B in your mixture, which contain this much of isotope B that was originally there, and this much that you added from the amount of spike you added. And by knowing the ratio of the 2 isotopes in the unspiked sample, and the ratio of the element of the isotope in the spiked sample, and the number of moles of spike you added, you can use this formula to determine exactly what the concentration is in your sample. And the beauty of this is you're doing this in your sample. There's no standard curve, there's no nothing. All you need to know is the ratio of the isotopes here, the ratio of the isotopes here, and the concentration of the element that you're adding. And so for anybody who cares about doing the most accurate kinds of measurements and samples that really matter, like they had to do when they were aging the Earth, because a 2% difference in the concentration and accuracy would result in, half a billion years error in their calculation. And so they had to measure it really, really accurately. This is how they did it. Right? And this is still one of the methods that's most commonly used to do that. Okay. So now I want to kind of move forward and talk about a few examples of things, right? So you guys saw something like this in marine analytical ladders, boxes, big instruments, that cost a lot of money. These are the ones that have, you can tell, because they have the little window here where you can see the plasma when it gets lit, right? The arc plasma. And another kind of mass spectrometer, which is upstairs from one you saw, which is a very common one, which is the one used, the type used when they were doing some of those measurements in geological science at the ancient Earth, is what they would call a solid source. Rather than in this example, rather than have your liquid sample that's pumped up and ionized in a plasma, you take a tiny drop of your sample and you put it on this wire. It has these two poles, and this wire, this thing's about that long. It's a skinny little wire made out of rhenium, and you would drop your sample on there and evaporate on that wire in the presence of some other ionizing, enhancing agents, and dry it down. And take 10 or 20 of these that you load separately, and load them in the sample chamber there, and close it and pump it down for 24 hours to get a low vacuum. And then you apply a potential to these two poles that would resistively heat this, and you would ionize your sample off that wire due to resistant heating. And then here you could do 20 samples in 3 days, as opposed to 20 samples in 3 hours, right? So the technology is advanced, though this is still necessary for some applications, but it's not as common use as it used to. So now I want to talk about some examples of how this works. And this is the isotope ratio measurements, and you would know, if you had a goal of wanting to measure isotopes, how would you do that? What kind of instrumentation would you need to use? Mass spectrometry, right? If you're measuring isotopes, to distinguish isotopes, you know you have to measure, or you have to use mass spectrometry. And the kind of mass spectrometer that you would use would depend upon what your application or need was. And mass spectrometers are commonly used in a lot of different fields. And I'd say 2 or 3 students from this class every year, when they graduate, go into some environmental chemistry or geochemistry job where they start using mass spectrometry to make measurements of isotopes and analytes in environmental samples. Because it's a roughly, it's a growth field. There's a fair number of jobs that they're doing that, and students that come with some kind of background in analytical sciences would go and are competitive for those jobs, and they're doing measurements of mass spectrometry for a lot of different kinds of applications. And one of the applications I want to talk to you about from the last 20 minutes or so is how we link environmental health to disease in people or animals.